Hi everyone. I'm super excited to be here. It's great to be back in Saint-Flour. Thank you very much to the organisers and to the scientific committee for the invitation to speak here. I'm going to be talking about scaling limits of random trees and random graphs, and I thought it might be helpful to start by saying what I mean by a scaling limit so that at least the title makes some sense. So imagine just for the sake of the argument that you've got a sequence of random variables an. Okay, so these are indexed by n and they're going to be growing in some sense as n gets large. Okay, so I'm going to say that this sequence has a scaling limit. If I can find some sequence of real numbers, let's call it little an, such that if I divide an by little an, then that converges in distribution as n goes to infinity to some limit, let's call it a. Okay, so you've certainly all seen an example of a scaling limit in that the central limit theorem has precisely this form. Okay, so I take the sequence an to be, let's say, a sum of centered IID random variables with finite variance, and you need to divide by, so square root of n times the standard deviation, and you get convergence in distribution to a random limit, which is the Gaussian distribution, so normal 0, 1. Okay, so I want to think about scaling limits of sequences of more complicated random objects, but this is somehow the thing that you should have in mind as being the basic example. And if you like, what I'm going to do in this course is just really complicated versions of the central limit theorem. Okay, so bear that in mind as we go forward. So we're going to have sequences of random objects taking values in some metric space. Okay, we're going to have some sensible notion of size so that we can rescale. And we're going to think about rescaling and taking limits. So there's a version of this where the limit on the right-hand side is deterministic. Okay, and that's also valid, but I don't really want to think about that as a scaling limit. I want to think about having a random quantity here in the limit in distribution. Okay, so moving on from the central limit theorem, you've also seen a more complicated sort of function-valued version of this. So if you think now about a random walk, and think about Donska's theorem, so again, take centered finite variance step sizes, then if you think about the function-valued object, you get convergence in distribution to a Brownian motion. Okay, so I'm going to be thinking about random quantities here, which are going to be tree-valued or graph-valued. Okay, so we're going to spend quite a bit of time setting up what it means to be taking a limit. So what's the right topology to put on the space of trees or graphs in order to think about taking such a scaling limit? And that will probably be mostly in tomorrow's lecture, I think. So where possible, I'm going to try to remain as concrete and hands-on as I can. Sometimes that will come at the cost of generality. So I'm not going to do things in the most general possible setting because I'd like you to develop some intuition about the objects that we're dealing with. And I think that's probably done usually best in the first instance through kind of simpler cases. So I'm going to try to keep it as kind of concrete as I can. There are a few kind of general principles that I'm going to make appeal to. So one of the things I find beautiful about this subject is it's a nice interplay between combinatorics, probability, analysis. But I want to emphasize that we're going to be dealing with random objects where we might say, pick a tree from a particular family uniformly at random. Just in and of itself, that's not a very helpful way to go about things. Generally, once they're picking a uniform object from a very large set, and without having some sensible way to actually do that, we can't really get our hands on those objects. So somehow being able to analyse random objects is often very closely related to the possibility of actually generating them in the first place. And so there's going to be quite an algorithmic side to what I describe in these lectures. And I hope to show you how that combination of sort of algorithms plus stochastic process theory lead you to be able to understand these scaling limits that I'm describing here. Okay, so let me give you a sort of rough plan for the lecture course. So today I'm going to give you a first glimpse of the Brownian continuum random tree. So please don't worry if that's an object you've never met before. My intention is that this lecture is for you. So a first glimpse of the Brownian continuum random tree. Okay, as I said, so probably tomorrow we're going to do the setup for thinking about these things, and in particular, what sort of limit objects are we going to be talking about? So these are going to be a collection of objects called R-trees, and I'm going to introduce the right topology for thinking about them. So this will be the Gromov-Hausdorff-Prokhorov distance, or generated by, can I spell Gromov-Hausdorff-Prokhorov? Okay, so then I'm going to talk about a sort of reasonably broad family of models of random trees which converge to the Brownian continuum random tree. Which I'm always going to abbreviate as BCRT, because otherwise I'm going to spend half of this lecture course just writing Brownian continuum random tree. So once we've done the convergence theorem, I'm going to talk a little bit about some properties of the Brownian continuum random tree, because I'm going to use them in the rest of the course. And then I'm going to turn to graphs. So the first model of random graphs that we'll think about are uniform random graphs, random connected graphs. With given size and number of edges. And then finally, we're going to turn to the critical Erdős-Rényi random graph. And its scaling limit. So I'm in the process of writing a sort of final lecture, which has a kind of vestigial page in the notes, which is called Perspectives. So that's going to be a little bit different. So my intention is to do that on slides. So I'm thinking of this as kind of the basic theory. And my hope is that once you've followed this course, you'll be in a good position to read any of the papers that I'm going to mention in the Perspectives section. So there's a big literature. I'm not going to attempt to do a comprehensive survey, but I at least want to give you some ways into what there is, and in particular I want to mention some open problems. So I think you'll have noticed that my notes are by far the shortest of the three sets, so they're probably also the most recently prepared. They're definitely a work in progress. I've spotted about 1 million typos, so I'm going to try and upload this afternoon a version that corrects the typos that I've found, but please do come and tell me about any. Maybe compare against the version that I'm going to upload to the webpage, just to check that I haven't already spotted them. But so I'm going to put an updated version on my webpage. So ac.ac/tilde, first 8 letters of my surname, and then sans floor. So for the moment, there's just the copy that you've got in front of you sitting there. So please do let me know of anything you spot. I haven't found anything major yet, but that may also be there. So throughout the notes, I've put a number of exercises. My hope is that they're not too crazy hard, and the intention is that they should hopefully help you to understand the concepts that we're talking about in the lectures. Okay, so I think without further ado, I'm going to turn to the first glimpse of the Brownian CRT. Let me also just say that I absolutely endorse everything Jean-Christophe said earlier about how to make the most out of such a school. please do come and talk to me. Do talk to each other. Don't hesitate to interrupt me in the middle of the lectures if I say something that's at all unclear. And likewise, please do come and talk to me at the end if there's something that you'd like to know more about. Okay, so I want to start with a particular discrete model that has some particularly nice properties. So I'm going to start with a particular model of binary trees. Okay. So, set of objects that I'm going to be talking about, roughly speaking, so Tn bin. So this is going to be the set of planted binary plane trees, and I'm going to explain each of these words in turn with n leaves. Okay, so I'm always going to think about rooted trees, and that's the case here. Okay, and planted means that coming from the root, which I'm always going to draw at the bottom, there's a single edge. Okay, and then every other vertex is going to either have 2 children or 0 children. Okay, so that's what I mean by binary. So here's an example of the n equals 3 case. Okay, so I've got 3 leaves. Okay, my tree is binary in the sense that every vertex apart from this root has 2 or 0 children. Okay, and I want to think about plane trees. So my trees have a planar embedding, and it matters whether this subtree is on the right or the left. So that's not the same thing as this tree. Okay. So in fact, those are the 2 instances of, so that is precisely T3 bin, are those 2 trees. Okay, so for n equals 1, things are simple, there's only one possibility. And likewise for n equals 2, there's only one possibility. Okay, so this is the first non-trivial situation. Okay. So I'm going to refer to this edge at the bottom as the plant edge. I don't know if that is consistent with anybody else's terminology, but I just want to distinguish this edge at the bottom. Sometimes we're going to want to include it, sometimes we're going to want to throw it away. You'll see that that's not going to make very much difference to anything, but for the moment it's convenient to have it there. Okay, so I'm going to be thinking about random trees sampled from Tn bin. Okay. So let me just say a couple of things. So any element of Tn bin has, so it's got n leaves by definition. So it's got n minus 1 internal vertices, so non-leaves and non-root. And necessarily 2 n minus 1 edges. Okay, and one of the nice things about this model is that those are common properties of every tree in this set. Okay, so there are some things here which, even once I sample a random tree, are going to be deterministic. Okay, so I'd like to add a little bit of extra structure here. So I'm going to let Tn bin star be the same thing, but where I label the leaves by the numbers 1 up to n. Okay, so this, for example, would be an element of T3 bin star. So same trees, but with a labeling of the leaves by, and let me introduce a piece of notation that I'll use throughout the course. So square brackets n is going to be the first n integers. Okay, so to any one of these trees here, there are 3 factorial different ways to label them. Okay. So that probably feels like a silly thing to do. And basically, the general principle that I'm going to appeal to is that it's easier to study random trees that have fewer symmetries. Okay, so I'm going to use this leaf labeling to break the symmetry between the leaves. Okay. So, quick proposition. I don't know if this is bad form. The very first proposition I'm going to give you is something I'm going to leave as an exercise to prove, but there's quite a detailed sort of scaffolding of the proof in the notes. Okay, so this is maybe not the most important point. But so how many of these trees are there? We can enumerate. And this is one of the myriad families of combinatorial objects which are enumerated by the Catalan numbers. So this is the n-1th Catalan number. So let me define Catalan k to be 1 on k plus 1 to k, choose k, for k greater than or equal to 0. Okay, so this is the kth Catalan number. It is astonishing how many things these things count. Okay, and then not surprisingly, because all I did was add a leaf labeling, if I want to enumerate the sort of star version of my trees, then what I get is n factorial times cat n minus 1. And so that gives me 2n minus 2 factorial divided by n minus 1 factorial. Okay. So why do I want to talk about this particular family of relatively simple trees? Well, because there's an extremely nice way, sort of miraculously simple way, of constructing a uniformly random element of this set. Okay, so this is something called Rémi's algorithm. It comes from 1985. Basically, today's lecture is going to be extracting consequences from Rémi's algorithm. Okay, so like I say, this is a miraculously simple algorithm for generating a uniformly random element of this. Okay, so I'm going to start from a single edge. Okay, so maybe let me do this over here. I should have said, just by convention, I'm going to label the roots here by 0. Okay, so my leaves are going to be labelled by 1 up to n, and I'm going to label the root 0. Okay, so I'm going to start from a single edge whose endpoints are labelled 0 and 1. Okay, so let's call this T1. Okay, and then repeatedly at subsequent steps, so suppose I'm at step n, I'm going to come along with a new edge with a leaf on the end, and the new leaf is going to be leaf n. Okay, and from whatever I've built so far, I'm just going to pick one of the edges uniformly at random, split it in two, choose a side left or right, each with probability half, and then insert a new vertex in the middle with my new edge and leaf at the end. So here I've really only got two choices. So with probability half, I go right. With probability half, I go left. So suppose I go right. Okay, so at the next step, I come along with my leaf labelled 3. I say choose an edge uniformly at random, suppose this one. Okay, choose left and right, each with probability half, and then glue in my new leaf and edge. Okay. So at each step, just choose a uniformly random edge, and then split it, choose left or right, and insert the new thing. Okay, so I think you'll agree that this couldn't possibly be simpler. Okay, so the edges in my picture have got lengths just because I'm running out of space, but they don't have any meaning. I'm just thinking about this as a graph theoretic object for the moment. Okay, but the left-right, this planar ordering does matter. Okay, and I think you can see how to convert this into something that's sort of drawn in a nice canonical way. Is everybody clear what I mean? Okay, so let me write down the rest of the algorithm. So at step n greater than or equal to 2, pick an edge uniformly at random. Divide this in 2 and insert a new edge and leaf labelled n to left or right, with each with probability of half. Okay, and then call the resulting tree Tn.
So now for next step we have 5 edges to choose right.
Yes.
And for every edge we have 2 sides.
So I'm always adding 2 extra edges at each step. 1 because I split an edge in 2, and then I add another edge with the new leaf on it. Right? So I always increase the number of edges by 2.
So now in the graph we have 5 edges.
Yeah, exactly. So 1, 2, 3, 4, 5. Okay, great. Yeah, and that is consistent with the fact that we always need to have 2n minus 1 edges. Okay. Right, so, I mean, my claim is that this produces a uniformly random element of my set. But let me first emphasize that if that's true, and it's true for every n, then not only have I generated a uniformly random element of the set, but I've got a coupled family of them. Right? As n varies, I'm uniform on t bin n star for every n. Okay. So proposition 2.2. This is due to me. Is that for all n greater than or equal to 1, Tn is a uniformly random element of Tn bin star. Okay, so what's lovely about having this leaf labelling is if I give you a particular tree that's labelled on its leaves by 1 up to n, there's only one pathway that can get you to that tree. Right? You have to have inserted each of the leaves in the right place and to left or right correctly. Okay? So there's only one possible way you might have achieved that, and that's the beauty of the leaf labelling here. Okay, so if I didn't have the labelling of the leaves, I'd have to think about the different ways in which I might achieve a particular binary tree with n leaves. Okay, and I'd have to think about different complicated pathways through my algorithm, whereas here, there's only one way to get a particular tree. So there's a unique pathway through the algorithm to any fixed element of the set that I'm aiming at. Okay. So at step k plus 1, how many choices do I have? Well, I've got 2k minus 1 edges in my k tree. Okay, so I need to pick one of those, and I need to pick a side. So there are 2 times 2k minus 1 choices. So let me call it to add the leaf edge. Okay. hang on a sec. Okay, and those possibilities are all equally likely. So the probability that I generate the right thing after n steps so the probability we generate the right tree is simply the product over those probabilities. And well, if I rearrange that, I can write it simply as, well, if I multiply top and bottom by k, and I can see that on the bottom what I'm generating is just 2n minus 1 factorial, and on the top what I'm generating is n minus 1 factorial. Okay, which is precisely, 2n minus 2. It would help if I got the right answer. So that's precisely 1 on the size of the set. And so indeed, I have generated my tree with the correct probability. Okay. So where have we got to? So I've got a very simple algorithm for generating a uniformly random element of this set, and indeed a coupled family of these random trees. Okay, and what's nice about that is that I can really think about what's going on in these trees as n goes to infinity very concretely. Okay, so I'm going to study the properties of this tree Tn as n goes to infinity in this coupled family. So my aim is to investigate the geometric properties of this family Tn greater than or equal to 1. Okay, so when I say geometric properties, what sort of thing do I mean? So I'm going to be interested eventually in thinking about trees as metric spaces, right? So you can think of any graph as a metric space. How do you do that? Well, you take the vertices of the graph to be the points of your metric space. And then there's a natural distance, which is simply the graph distance. So that's how many edges are there on a shortest path between your two vertices that you're interested in looking at. Okay, and that's going to be the perspective that we'll take on these objects. And of course, when you're thinking about trees, there is only one shortest path between a pair of vertices. Okay, and so it's kind of completely clear what the distance between two vertices ought to be. Okay, so we've got some labels. So let's make use of them. So let me think about distances. And what's lovely, sorry, Jean-Christophe.
At the beginning, you told us that it's important how it's embedded in the plane.
Mm-hmm.
But then if you think about it as a metric space, then this is going to be lost. Is that part of the plan?
Yeah, exactly. So, I mean, my planar embedding is really, again, one of these, let me try to get rid of some symmetries issue so that I can count easily. As you can see, the counting is particularly simple because I've killed lots of symmetries. But actually, when it comes to thinking about these objects as metric spaces, I really don't care at all about the planar embedding. I really just care about the geometric structure. Okay, so what's particularly lovely about this model is that we can think about things in terms of just balls in urns. So really simple, kind of basic probabilistic models. Okay, so as I said, we've got some labels, so let's make use of them. So the first thing I want to think about is a quantity I'm going to call Bn, which is just the number of the edges on the path between my root labelled 0 and the leaf labelled 1. So the number of edges on the path from 0 to 1. Okay, so this feels a bit special, except that actually if you think about it, the leaf labelled 1 is playing exactly the same role as each of the other leaves. So I'm not really losing any generality by looking at the leaf labelled 1. And indeed, were I to pick a uniformly random leaf, that would have the same distance distribution. So I'm not losing anything by just looking at one. Okay, this is going to tell me something more interesting in general. So this is in the tree Tn. Okay, so obviously in T1, this distance is just 1, and it's gradually going to increase as we add edges to the tree. Okay, so I guess I learnt about this stuff from a paper by Philippe Marchal, who's over there. Philippe, you can tell me if this is the right attribution to attribute the next lemma to you. Okay, so I'm going to try to stick to the numbering in the lecture notes. So. Okay, so it turns out, and we're going to prove this in a moment, that if I rescale this random variable bn by the square root of 2n, then it converges almost surely to some limit L as n goes to infinity, where in fact we can specify completely what the distribution of this random variable L is. So L has the Rayleigh distribution, which you may have come across before. If not, this is the distribution with probability density function. So FL of x is x e to the minus x squared on 2 for x greater than or equal to 0. Okay, so we have a limit and distribution for this distance between 0 and 1 when we rescale by square root of 2n, and indeed we've got a really nice limit and distribution. Okay, so if you like, this is a first scaling limit for this tree. Okay, so maybe to come back to say to something that I said in my sort of introductory remarks. So I said that we were going to be doing something that was a bit like a really fancy version of the central limit theorem. Well, there's the central limit theorem scaling, right? We've got the square root of n already popping up. So although my tree has got n vertices in total, in fact 2 n vertices in this model, the distances in the tree, at least in some sort of typical, what's the distance from the root to a typical leaf, those are varying like square root of n. Okay, so let's give a quick proof of this. What am I doing for time? Okay, so I want to consider the evolution of this Bn as a process. So my claim was that this thing is evolving like an urn. So what's the urn? Let's think about what happens here. So if I look at the distance between 0 and 1, okay, so either I add, so imagine that we've got some stuff coming off here. So either I pick one of these edges along the path from 0 to 1, okay, in which case I'm going to increase the number of edges along this path by 1. And I'm also going to keep track of the number of edges which are not on the path, right? If I keep those two pieces of information, then I'm sort of complete, okay? And I'm going to add one edge off of the path, okay? On the other hand, if I add somewhere else, I just add 2 edges somewhere else. Okay. So if I add a new leaf edge along the path, we add 1. Otherwise, add 0. So in particular, this is evolving like the number of black balls in a 2-colour urn which has the following replacement mechanism. So let's say black and white. where, so if I pick black, I'm going to try to keep to the colour of the board. My tendency is to want to think of this as a white ball, but this is a black ball. So if I pick black, then I'm going to put it back in addition with another black ball and a white ball. And on the other hand, if I pick white to start with, I'm going to put it back, but with 2 other white balls. Okay, so that's controlling what happens sort of off the path between 0 and 1. Okay, right. So how do we study urn processes? Well, using martingales. Okay, so where's the martingale? So note at step n, there are always 2n minus 1 balls. Okay, so the expected value of bn plus 1 given bn. So either I pick one of my black balls, which has got probability bn on 2n minus 1, and in that case, my number of balls goes up by 1. Otherwise, it stays the same. So with the complementary probability, I just get bn. Okay, and if you put all of that together, what you get is 2n on 2n minus 1 times bn. Okay, so if I want to make this into a martingale, I want to somehow undo this multiplication by a factor of 2n on 2n minus 1. So let me define a sequence that's going to do that for me. So I want to end up with a mean 1 martingale. Okay, you're possibly used to thinking about mean 0 martingales. I want a mean 1 martingale here. Okay, so define real numbers bn by exactly the deterministic version of this relation. So by bn plus 1 is equal to 2n on 2n minus 1 times bn. Okay, and of course I want to start from 1. Okay, so in particular, what does that give me? It gives me 2 to the 2n n factorial squared divided by 2n factorial. Okay, and if you hit that with Stirling's approximation, what you get is something that looks like the square root of pi times n. Okay, so I've got a sequence which is growing roughly like square root of n. Okay, so this is looking hopeful for the renormalization that I was thinking of taking in order to get convergence in distribution, or convergence almost surely. So this is as n goes to infinity. Okay, so in particular, this is exactly what I need in order to make this thing a martingale. And indeed, it's a non-negative martingale, so the almost sure martingale convergence theorem gives you that it has an almost sure limit, basically for free. Okay. Okay, so if you want to work out what the law of that limit is, and to some extent I'm a little bit less worried about precisely what that law is for the moment. In some sense, the thing I'm really interested in here is that square root of n is the right scaling to apply. But while we're at it, let's write down what the distribution of the limit is. So I'm not going to give the full argument here. So there's a bivariate generating function argument which gets you actually the exact distribution of Bn. And I've put a reference to that in the notes. So in fact, it's slightly easier to write down what the probability mass function of Bn plus 1 is. Okay, so this turns out to be k minus 1 on n times 2 to the k minus 1, 2n minus k, choose n minus 1, divided by 2n, choose n, not surprising that lots of Catalan-y looking things should crop up in this context. Okay, so that's for k between 2 and n. And indeed, you can kind of apply Stirling's approximation again. So I can think about what's the limiting density that this is giving me. So if you think about taking a k which is equal to x square root of 2n, okay, that's going to be the thing that's going to give you the nicest expression here. There are lots of 2's that would be quite nice to play off against. Okay, so if I look at this, it's going to give me a limiting density if there is one, and this converges. You can check from Stirling's approximation to the xe to the minus x squared on 2 that I claimed. Okay, so that identifies the distribution of the limit, and since we know we've got an almost sure limit, it must have that distribution. Okay, so that seems like a good place for a 2-minute break. The distance between my root and the leaf-labelled one is scaling like roughly square root of n. Okay, so what can I say about distances between other leaves, for example? So if you think about where we are at step 2, so we've got one of these two pictures, right? Either we've got this one, or we've got the one where 2 is on the right-hand side. But in terms of what's going on in the dynamics, it doesn't make very much difference. I'm going to evolve as 3 little subtrees, right? Okay, there's sort of what's going on here, what's going on here, and what's going on here. Okay, so if I think about this subtree that's spanned by these 3 leaves, I can now think about how these 3 distances, from 0 up to the middle, middle up to 1, and middle up to 2, I can think about how those 3 things evolve together, if you like. And what you can immediately see is, if you think about every time I add to this subtree, I'm just doing a new little copy of Rimy's algorithm, right? There's nothing that's telling me that I want to be anywhere in particular, right? So conditional on adding to that subtree, I'm just adding in the usual Rimy fashion, right? So I've got 3 little copies of the original problem. It's just that I'm adding edges, well, a number of edges which is dependent between the 3 copies, right? But once I know how many edges I add to a particular copy, that tells me everything I need to know. I then know how this distance works, because we just figured it out. Okay. So the game here now is to try and understand how many edges I add to each of these 3 copies, and then I know everything. Okay, so I want to consider the subtree spanned by 0, 1, 2, and how its lengths evolve. Okay, so as I said, given the sets of leaves, I've just got 3 little copies of Remy's algorithm. Okay, so it suffices for me to understand the number of edges that go into each of these copies. And what's lovely is, again, that's a little urn. It's a little 3-colour polyaz urn, in fact, because what happens? Okay, I pick one of these 3 colours, okay, an edge from one of these 3 sets, okay, and I add, well, I put it back, and I add 2 more edges of the same colour. Okay? So the number of edges in each subtree behaves like a 3-colour polyaz urn. Okay, so let me write Rn, Gn, Bn for red, green, and blue. I probably do have the colours, but maybe imagine that I've got different colours of chalk for the 3 different trees, because otherwise this is going to take me forever. Okay, so red, green, blue. Okay, at each step, pick a ball, and then put it back with 2 more of the same colour. So this precisely describes the evolution of the number of edges in each of these 3. And another feature of this is that I don't really care which of the subtrees is the red one, which is the blue one, and which is the green one, because everything's completely symmetric by relabeling. Okay? And this property of exchangeability is something which comes up all over the place in the study of these particular trees. Okay, so for definiteness, let's start from time 0 with a single ball of each colour. Okay, so I've left the proof of the limit here as an exercise in the notes, because this one really is relatively straightforward. So again, you need to find a martingale, but it's a rather simpler martingale to think about. Okay. So let me just remind you of the definition of the Dirichlet density, just in case that's something you've not seen before. So I'm going to let dir of alpha 1, alpha 2, up to alpha n, or alpha k, let's say, denote the Dirichlet distribution. I suppose I'm in France, so I should say Dirichlet. So this is the distribution which has density. So there are some constants which involve gamma functions. Not too important what that is. And then the important point is that this is x1 to the alpha 1 minus 1 up to xk to the alpha k minus 1. But this is on the k minus 1 dimensional simplex. So I want my coordinates to sum to 1. So this is the set of vectors in r plus to the k, whose entries sum to 1. Okay. Right, and these things crop up all over the place as limits of urns. Okay, and that's nonetheless true here. So this is, let me emphasize, with respect to k minus 1 dimensional Lebesgue measure. Okay, so then proposition 2.4, which I will leave to you, is that, so at each stage in the urn, I've got 2n plus 3 edges present in total. Okay, and if I look at the proportions of each of the 3 colours, that's just this. Okay, then that converges almost surely as n goes to infinity to, let's say, delta 1, delta 2, delta 3, where this has got distribution which is Dirichlet a half, a half, a half. Okay, so this is again almost surely as n goes to infinity. Okay, so we have to have the same parameter here. There's so much symmetry that it can't possibly be different. Okay, and that's the limit that we get. Okay, so this is exercise 2.2 in the notes. Okay, so once we know how many edges there are, it's then easy for us to deduce the number of leaves, simply because these are just straightforward linear functionals of one another. Okay, so maybe let me put this here. It's not really working. Okay, so when we've got a tree with n leaves, that has 2n minus 1 edges. Okay, and so working backwards from that, we can see that the number of leaves in each of my subtrees just so this is 1/2 times Rn plus 1, so at step n, and so on and so forth. So there's a green one and a blue one. Okay, there's a small subtlety here, which is that I want to count this as the root of each of these two trees, and I want to count it as a leaf in the bottom tree. Okay? So it's a leaf here and the root for each of these top two trees, and then what I've written makes some sense. Otherwise, I've gotten off by one error, and I don't really care because I'm going to divide by n and take a limit, so it doesn't really matter. But for sort of cleanliness, let's have these three things be exactly copies of the original binary trees. So in particular, if I just look at proportions here, these are precisely converging almost surely again to the same Dirichlet vector. Okay, so if I come back here and I think about the evolution of this thing, so I'm adding leaves gradually as I go, what I end up with is proportions this much in each of my three subtrees. Okay, and we know how things rescale. Things rescale like the square root of the number of leaves. Okay, so I can just read off from this what the limiting distribution of these three lengths here is, right? Because I've got three little conditionally independent copies. Once I know what proportions of the leaves end up in each of my three subtrees, I can then tell you what the lengths of these edges are in the limit. Okay, so then writing, let's keep the same notation. So let's write ln R, ln G, and ln B for the lengths of these kind of special edges or special paths that I'm interested in, right? These three here. If I think about those as being ln R, ln G, and ln B, then, so these are for the lengths. What do I get? Well, I get that if I rescale by, again, 1 on square root of 2n, then this is going to converge, again, almost surely as n goes to infinity, to what? So I get a square root of lambda 1 multiplying a Rayleigh for the first tree, okay? Because I divided by square root of 2n, and what I should have divided by was square root of 2n delta, okay? So I've got the extra factor of root delta that I failed to divide by. Okay, and in the second one, I get square root delta 2, L2, and then square root delta 3, L3. Okay, so again, this is my same Dirichlet 1/2, 1/2, 1/2 vector, and then L1, L2, and L3 are IID Rayleigh independent of my delta. Okay, so already we've understood really quite a lot about how this thing is looking when we send n to infinity. Without really formulating what it means properly to take a limit of the tree, we've at least seen that for certain statistics of it, we can take limits. And the point is that there's a completely analogous argument that you can run. I'm not going to go through the details because I think now you've seen this, you could reconstruct it for yourself. What happens if I sort of stop this process when I've got the first k leaves present? Okay, so that gives me some random binary tree, okay? And it splits my big tree up into 2k minus 1 bits, okay? And each of those bits is again doing a little copy of Ramey's algorithm, and you get precisely the analog of this statement here. And again, there's some randomness now. I mean, even at this stage, we had some randomness to the left or right of whether 2 got attached to the left of the path between 0 and 1 or to the right of it. But apart from that randomness in the sort of combinatorial shape of the object we were looking at, nothing else mattered in terms of the Ramey dynamics. Okay, so let me just say, completely analogous argument. Works for the subtree that's spanned by, so 0, 1, up to k. So in other words, we get a random element, well, uniformly random, of, so T air, Tk bin star as a sort of starting tree. It's a sort of skeleton on which we're going to build, okay? And then I can think of the 2k minus 1 little subtrees that splits my tree into, and think about how the number of leaves that end up in each of those evolves. Okay. And starting from there, get 2k minus 1 little copies of Romier's algorithm. So in particular, the distances that you end up getting have exactly the same sort of pattern to them. I've got here independent Rayleighs multiplied by, and you can do the earn argument again, doesn't really matter. This again gives you a Dirichlet, but now with 2k minus 1 elements. Okay. So I've got another half an hour, is that correct? I think so. Okay. So I've put in the notes now a sort of subsection about something called the beta-gamma algebra. So this is a sort of collection of distributional relationships which turn out to be really powerful for doing calculations. I think it's something that there's probably not a lot of value in my going through on the board, because I think it's something you get a feel for by doing the calculations yourself. So there's nothing there that's not just elementary sort of change of variables type stuff. But I think it's better if I leave it as something for you to read through and have a go at the exercises, rather than me trying to sort of go through it on the board. So what I'm going to say here is a sort of proposition / exercise, if I can put it that way, which is a nice consequence of some of that beta-gamma algebra. But if you take nothing else from this first lecture, know that there's a really nice set of relationships between gamma and beta random variables, which crop up in all sorts of different places, and which are really useful as a computational tool. Okay. So let me try and squeeze that in here. So this is sort of proposition / exercise 2.4. Okay, so the first thing is just straightforward, and you can probably see it just from looking at the density, actually. So the first thing is that if L is a Rayleigh random variable, then it has the same distribution as the square root of an exponential half. Okay, so that's the sort of change of variables you can do in your head. Okay. Slightly more complicated than that. If I've got the situation I've got here, so L1 up to L2k minus 1 are IID Rayleighs. And so independent of my Dirichlet half vector. Okay. Then in fact, magic is the only way I can describe this. The thing that we're interested in here, this collection of lengths, I can rewrite as the square root of a gamma random variable times an independent Dirichlet with different parameters. So let me write it down. This is maybe getting too small to be visible at the back, but Anyway, it's in the notes. So this has the same distribution as the square root of a gamma k. I'm going to use capital theta for the new distribution. Let me put this up here. So I should say that I learnt about the beta gamma algebra for the first time in Saint Flour from an amazing course given by Jim Pittman, which contained approximately the sum of human knowledge. Right. Okay, so where? So my gamma k, which I'm taking the square root of, is gamma k a half and independent of this theta vector, which has the nicest possible distribution on the simplex. It's just completely uniform on the 2k minus, well, the 2k minus 2-dimensional simplex. Okay, so this is kind of magic, right? I've got, these things are all sort of entangled via the deltas, which definitely depend on one another. Okay, and I've got these independent things here. And somehow I can factor this as a product of two independent bits. Okay, one of which is the square root of a gamma distribution, and the other of which is another one of these Dirichlet's. Okay, so this is really the magic of the beta gamma algebra that enables you to do this. Okay. So all of this is heavily suggesting that there is some limiting version of Remy's algorithm sitting here. Okay? And that limiting version is called Aldous' line breaking construction of the Brownian continuum random tree, and that's what I'm going to show you now. So what this says is that rather than first fixing k and then thinking about generating these little subtrees and seeing how they evolve, let's just fix k from the get-go and think about how we can construct the lengths that we're getting out of Remy's algorithm as an almost sure limit. Okay, so what are the objects that I'm going to be looking at here? So I'm going to generate a sequence. So let's say script tk of trees, such that, so tk itself is, so this is going to be an element of my binary plane leaf labeled trees with k labeled leaves, but it's going to have one bit of extra structure, which is that I'm going to give it edge lengths. Okay, so in our original picture we just had, you know, graph theoretic trees where you might want to think of edges as having length 1 if they have lengths at all. But here I want to think of them as having positive real valued edge lengths. Okay. So this is an element of, so T K bin star endowed with edge lengths in 0 infinity. I'm going to use non-French notation for each of its 2k minus 1 edges. Okay. So let me give myself a little bit of notation just to ease things up here a bit. So I'm going to write, hopefully this is fairly intuitive notation, I'm going to write shape of tk to mean just the element of tk bin star. Okay, so that's just the combinatorial part of this thing. And I'm going to write lengths of tk for the vector of edge lengths. So you'd be quite within your rights to complain about me not specifying what order I'm listing edge lengths in here. So let me sort of take a convention. So here's a sort of element of 1, 2, 3, 4. So T5 bin star with edge lengths. So for definiteness, let's list these lengths in the order that I encounter them for the first time when I do a sort of clockwise contour of the tree. So if I did that with this tree, that would mean this was edge 1. This one here is edge 2, 3, 4, 5, 6, 7, 8, and 9. Okay, but what I'm about to claim in a moment is that it really doesn't matter how I label them because they're going to end up being exchangeable random variables. Okay, so however I relabel them, it's not going to affect the distribution in a moment, as long as I don't do that in a way that depends on the particular lengths that I've got. Okay, so what's the algorithm? Okay, so let's let E1, E2, and so on be IID exponential half. And set CK to be the square root of the sum of the first k of them. So I sum up EI from 1 to k and then take the square root. And then again, the algorithm is super simple. I'm going to take a single edge of length C1 with its endpoints labelled as usual. Okay. And then at each subsequent step, so step k, I'm going to attach a new stick, if you like, of length ck minus 1 to this object that I've created. So to each side, left and right, each with probability half, and to a uniformly chosen point over the whole object that I've created so far. So for k greater than or equal to 2, attach an edge of length, so ck minus 1 to a random point chosen. So let me call this T1. So this needs to be chosen uniformly over tk minus 1 with equal probability to left and right of the stick that I choose to attach to. And label its other endpoint by k. And that's going to give me the tree tk. Mm-hmm. Nope, I'm going to cut it at a point chosen uniformly. So let me run a sort of run of this algorithm on the board, and then you'll see. Okay, and let me also do one other thing, which is start by drawing out sort of the positive reals. And let me draw the CKs on this positive real axis. Okay, so C1 is somewhere here. Okay, and these guys are increasing, right? They're random, but they're increasing. Okay, and one thing you can see is that they're getting stochastically shorter as I go. These distances between successive points are getting stochastically smaller as I go rightwards. Okay, so you can represent these points in terms of an inhomogeneous Poisson point process, and I've gone through, there's an exercise in the notes that will take you through that calculation, but I think this is the most elementary way to present this. Okay, so what do? So I start from a single point, a single edge, which has this length C1. So if you like, you can think of it as this line segment here. So I now take the second kind of chunk of line segment, and this is just now a real valued length. So I've got a perfectly good Lebesgue measure on it. Okay, so let's pick uniformly according to the normalized Lebesgue measure on that object. So I'm not splitting in the middle now, I'm splitting at a uniformly chosen point. Okay, and then I choose left or right, each with probability of half. So let's go here. Okay, so this is 0, this is 1. This thing has length C1. This is going to be labelled 2 here. And this stick here has length C2 minus C1. Okay, and then I come along and I have the length C3 minus C2. Okay, and I'm going to glue that somewhere chosen uniformly at random from this object that I've created so far. So let me put it here, just so that I don't run out of space. Okay, and that gives me the third tree in my sequence. So does that clear up the issue about where I'm gluing? Okay, good. Okay, so if you like, we can actually kind of sample these gluing points already in this picture up here. So what do? So I've got this length here, and I'm going to glue it somewhere uniformly on this line here, right? So really all I'm doing is I'm saying, take this and pick according to normalized Lebesgue measure on here, and that's the place that I'm going to glue that. Okay, and then I can go along and do the same thing. So this chunk here is going to get glued somewhere chosen uniformly from all of this line here, except that this has now been glued sideways. Okay, but nonetheless, so this is going to get glued the way I've done it somewhere here. Okay, and so on and so forth. So it could be that this stick, the next one that comes along, gets glued, say, here. So what would that correspond to on my drawing? That would correspond to doing something like this. So that's the tree labelled 4. And again, at each step, I've got this coin flip. Do I go above or below, left or right, the line that I've picked?
But does it matter, like, where do you glue the thing on the tree? So there's this distance.
Yes, and I'm gluing uniformly. So I've got a finite length measure for the whole thing that I've created so far, and I pick a uniform point according to that length measure. Yeah, exactly. So I've got, this really is in the continuum. We're no longer in. Go ahead.
In the above line, is it clear on which side you glue it if you draw it like this?
No, so I've lost the left-right. So there's an extra coin flip for each attachment in this picture. Right, and that's because I want to end up with an element of TK bin star at the end of the day. So I need this left-right ordering. Is it clear what's going on now? Now's your moment to ask.
I also know, but it's not like the edge, for instance, with lip 1 gets smaller and smaller as time goes?
No, so this edge stays now the same length. So what I've done is I've sampled its limiting length from the get-go.
But the remaining parts go smaller and smaller?
So this part's getting smaller and smaller. So this thing is getting hairier and hairier and hairier as I go on. Right, so I'm adding. You have to think that these chunks here are stochastically getting shorter and shorter as I go rightwards. So eventually what I'm doing is I'm just adding sort of tiny hairs all over the place. Okay, more and more hairs. And the hairs are sticking on top of the other hairs. Okay? That makes sense? Okay. Right, so I'm getting a little bit short on time. So I've got 10 minutes. in which I want to at least kind of state a couple of theorems. So first thing, so proposition 2.7, this really is the limiting version of Rémi's algorithm. Okay, so firstly, if I think about the sequence of shapes that this is giving me, okay, so just think about the combinatorial object, okay, not with the edge lengths. This really is exactly doing Rémi's algorithm. Okay, and secondly, if you look at the limiting lengths that you get, or rather if you look at the lengths of tk, which are in no sense limiting, they're just given to us from the get-go, then this has the same distribution as my square root of a gamma k times a Dirichlet 1 vector. Okay, so this again is gamma k a half, and this is uniform on the simplex, and these are independent. Okay. So this really is generating for us both the correct shape, but also, so in the combinatorial sense, but also the correct edge lengths for what we get when we take the limit in Rémi's algorithm. Right, so I think I don't have time to go through the proof, which in any case I was only going to sketch, because what I'd like to do is talk a little bit about the limiting object that this gives us. Right, so I've got a family of trees with edge lengths here. So I've got this combinatorial aspect and this very much real-valued aspect. And I want to think about, well, how can we make sense of taking a limit in k? Okay, so one way to think about Aldous' Brownian continuum random tree is as the limit as k goes to infinity of this construction. Okay, so just keep adding edge lengths forever. And what does that give you? And there's a question that we should immediately ask ourselves here, which is, does this thing converge in a reasonable sense? Right? So it could be the case that these little hairy bits kind of pile up on one another and kind of wander off to infinity. Right? So there's a question about whether the object that we get remains compact in some reasonable sense. Okay? And in order to talk about compactness, I'd like to be working in some sort of sensible metric space. So let's do that. So this is really going back to Aldous' very original conception of this object. So he thought about his Brownian continuum random tree in the first of 3 landmark papers that he wrote at the beginning of the 90s as being a subset of L1. Okay, and there's a good reason for doing that, which is that it plays very nicely with this construction. Okay. So we want to take, okay. So I want to take a limit as k goes to infinity. Okay. So think about tk as an element of, so L1, by which I mean sequences x such that the sum of the modulus of xi is finite. Okay, and I'm going to endow it with the usual L1 norm. So in order to do this, let me give myself some notation for the sort of standard basis vectors. So this is going to be just the sequence that's got a 1 in the first coordinate. E2 is the sequence that's got a 1 in the second coordinate, and so on. Okay. And then what I'm going to do is I'm basically going to put each stick in a new coordinate. Okay? So let's take, as a convention, C0 and A0 to be 0. And I'd like to use this sort of vision for the points where I attach to. Right? So the C's are called C's because they're cut points, and I'm going to call A's the attachment points. And I'm going to think about them as being sampled from the positive reals. Okay, so this one is A1, this is A2, this is A3. So AI is the point at which the edge to I plus 1 attaches to the ith tree. Okay, so AI is taking values. Actually, I'm going to think about it as taking values in the positive reals in this picture. Okay. So in particular, I'm thinking about AI as being uniform, so conditionally on CI, being uniform on the interval 0 up to CI. Okay, so I hope that's clear. Okay, so I'm now going to define a function from R plus, from this picture up there, into L1 as follows. So firstly, I'm going to map 0 of the positive reals to the 0 of L1. And then I'm going to map ft to, let me write this down and then explain. So f of gay k plus t minus ck ek plus 1 for okay, so this is going to capture every t in R plus. So what do? I start from 0, okay, and then I'm going to find myself in this first interval up to C1, okay. So I'm starting from the 0 of L1, and I'm just linearly embedding in the first coordinate, right? So I'm just increasing in the first coordinate up until I get to C1, right? And then I'm going to jump to whatever f of the attachment point was. So that's some point along this first coordinate. And I'm going to start embedding the next bit in the second coordinate. Okay? And then when I get to the next cut point, I'm going to jump back to wherever I embedded in L1 the next attachment point, and I'm going to start growing out in the next coordinate from there. Okay? Okay, so this seems like a sort of reasonably sensible way to go about sort of sticking this thing in some canonical metric space. Okay, and so there's a question which arises, which is, you know, if I send k to infinity, am I getting some sort of nice closed thing? And the answer is no, so I need to take the closure. Okay, right, so this is going to give me something which is sort of missing some limit points. Okay, and I'm going to add them in order to get my definition of the Brownian continuum random tree. Okay, so TK I'm going to think of just as what happens if I embed up to the kth cut point. So then Okay, I'm abusing notation. This is not the same object as I was thinking about before. This is my L1 version of the thing that we were talking about before. So this is the function of the image, or so the image under this function of the interval 0 up to ck. And I'm going to let the thing I'm really interested in be f of positive real line. And I'm going to take the closure in L1. Okay, so how am I doing for time? Oop, right, I'm going to take 2 more minutes if that's all right. Okay, so definition. Any metric space which is isometric to this is a Brownian continuum random tree. Okay, so it should be completely not obvious to you at this point what this has to do with the Brownian motion. Right? There is no Brownian motion in this picture for the moment. All I did was I took some line segments in R+, and I glued them together in a relatively simple fashion. I think about as simple as you could cook up and get something kind of non-trivial. And I'm claiming that this has something to do with the Brownian motion. So we'll see either tomorrow or the day after why that's the case. But I think as a first introduction to this object, at least thinking about sort of the picture I drew on the board, this is by far the easiest way to get a hold mentally of what this thing is looking like. Okay, just think about it as line segments that you've glued together, and this sequence tk is going to give you a nice approximation to some limit object, which is itself a little bit more complicated. Okay, so let me just say a couple of things about this that we can read off this construction. Okay, so I haven't proved that this is a compact object, and I'm not going to go through that in the lectures, but I've put in a more detailed proof of that in the notes than you will find in Aldous' papers. I found that there were parts of his proof which were a bit quick for me to understand, and so I wanted to sort of go into those in more detail. So you'll find that in the lecture notes. But one thing that is clear from this construction, so if you believe that this is a nice kind of compact object to be thinking about, is that it must be binary. Because I'm never going to glue to the same point twice, or at least with probability 1, I will not pick the same point twice, because I'm always picking according to Lebesgue measure. Okay? So in particular, I'm never going to have the opportunity to create a branch point which splits me into more than 3 connected components for the space. So we think about the degree of a vertex being the number of different connected components into which removing it splits your space. You're never going to split into more than 3. And notice that the closure isn't going to affect that, because the closure can only ever attach points of degree 1 to this object. Right? So I'm never going to create a branch point by kind of adding in limit points. Okay, so the theorem due to all this is that this is indeed a compact object, and indeed this is going to be the scaling limit of a whole family of different random trees, and we'll do the setup for that in tomorrow's lecture. Thank you.